Welcome to the introduction to Nextflow for data-intensive pipelines. Today we'll be joined by Dr. Marco Della Pierre, he'll be presenting an overview of the fundamental concepts of the Nextflow framework. And we're also joined by Costa Service, who will present his experience with Nextflow to refactor an existing workflow. We're quite excited for our training today because this is our first hybrid event. So we have got individuals joining us online, welcome, as well as in the room. Welcome and thanks for joining us today. So before we get started today, we would like to acknowledge the traditional custodians of the land from which we're broadcasting, and that's the Whadjuk people of the Noongar Nation. And we would like to pay respects to their elders past and present, as well as extend that acknowledgement and welcome to any Aboriginal or Torres Strait Islanders who may be joining us today. So with that, I will hand you over to Marco.
Yeah, thanks, Sam, for the introduction. Welcome, everyone. And yeah, I have to share with you, this kind of excitement for finally having again a real live audience in the room today, which is a bit quiet right now, but it's really exciting after I think almost 2 years of virtual only event. It's really great to have the chance to have an exchange in person with some actual people. So thanks for being here today. So that being said, let me start with this first part of today's webinar on a Nextflow for data-intensive pipelines. So what I'm going to go through is an introduction to what we mean by data-intensive pipelines here at Pawsey, and then introduce some concepts around Nextflow and how to use it. And I will also show you some live demos of how to use Nextflow in practice before handing over to Costa. So this is an example of a scientific workflow the way we mean it. So it's taken from the bioinformatics domain. So as you can see from this diagram, it's kind of a collection of interdependent tasks that operate on your data. And in fact, you see here at the top left, there is an input point where you provide your data, and then there is a sequence of tasks that make up the entire workflow. Some of them are in serial dependencies, so you do one after the other one, but then you can have some more articulated logic. For instance, you can have some forking where the output from a task needs to be processed by multiple tasks, such as the case of the mapping context and blasting after the assembly step here. You can also have steps like the one here towards the end, where you are collecting and gathering outputs from multiple steps, forming the input for a single step that aggregates all of the previous data. And sometimes you also need some user input along the pipeline, as represented by these diamond blocks, where a user is requested to provide additional information before the pipeline can continue. And that also needs to happen before the final output can be collected. So this is just a kind of a simple example with just a bunch of tasks, less than 10, but some of these pipelines can become quite articulated. And so you can imagine that first of all, these workflows typically map a scientific protocol that is part of your research, and that's basically translation into computer language of this protocol. So it's very important that these workflows accurately map what you would like them to do, because an error in this regard might mean that the output you get don't really mean what you think they mean. So it's really important to set up these workflows and use tools to set up these workflows in a way that enable you to implement your scientific protocol the way you want to. And this is one of the aspects that are quite crucial to scientific workflows in a computational context, but there are other aspects, and let me go through this slide just to name a few others. we mentioned the several high-level tasks with dependencies. You can have flow controls, as we said. You may also need, for very long workflows, you may need to do restarting of the workflows, because maybe the cluster where you're running has some wall time policies, maximum wall time policies, and then you may need to be able to rerun the task starting from the last meaningful checkpoint. And sometimes you may need to do that because one of the tasks failed. It crashed, it produced a bad result. And then you need to be able to log these errors and be able to restart the workflow in an appropriate way. And so all of these aspects are kind of general features of workflows. They're not inherent to any specific ones. So it would be good actually to have to use a framework, a platform that that simplifies the burden of implementing all of these features for your own research. And last but not least, well, you can imagine that when you need to process larger and larger amount of data, the amount of work that is required to set up and successfully run to completion these pipelines becomes even larger. To our experience here at Pawsey, there's quite a few scientific domains that are actually relevant to this conversation. And here I'm just really naming a few, the ones that I've got the chance to engage with, but there's surely more than this. So bioinformatics, radio astronomy, planetary sciences, including the folks that are with us today, but also geosciences and data science, of course. So building on the previous concepts I just presented you, there are some very high-level desired features then that we would like to express when developing, designing, and then deploying a workflow. So the first one I have in this slide here is scalability, which basically means you may be starting the design of a pipeline on your own laptop with just a very small input data set. But then once the pipeline is ready for production and maybe you need to process a large amount of data, you might end up realizing that the laptop is not enough. Then you need to move the deployment of your pipeline to a larger workstation, or even a cluster, or even a supercomputing facility such as Pawsey or NCI, or even commercial cloud services. So it would be desirable that the workflow setup you have devised is able to easily allow you to scale your work in these terms with little extra work required. Then there is a reproducibility aspects, and here this relates to a few similar aspects. So one is reproducibility in time. So if I need to rerun the very same workflow on the very same data set 1 year from now, am I able to get the same results? Or, but there's also an aspect of portability that is kind of related. If I need to rerun the same workflow on a different facility, am I getting the same results? Or if my collaborators, if I'm willing to share my protocol and workflow with other people, with collaborators or other scientists, are they able to set it up, deploy it, and get the same meaningful results? And then there's also an aspect of data provenance, which means am I able to easily reconstruct and report on the story of a given data set? So when I am presenting some data outputs, am I able to also track back all of the processing steps they went through, starting from the original input data set? And there are also aspects of productivity for which I have a dedicated slide here. So the first item here is, I won't go into deeper detail today. So a large articulated workflow typically also requires a large software stack in order to be run, because very often each processing step of the pipeline might need different softwares. And so it would be good to be able to reduce installation and deployment times of software. This is not, as I said, this is not solved by workflow engines, but it can be solved by other technologies such as containers, just to mention those. But then there's also productivity aspects related to the actual scientific pipeline. And as I said, we mentioned some inherent features that are generic to each pipeline, sorry, to any pipeline, like flow control, error handling, checkpointing, logging, and scalability to high throughput. It would be good if we could avoid having to code all of these features, all of these abstracted features every single time we need to write a new pipeline. So it would be good if there were a framework, a software framework that does that for us. So that all we need to do is really just to focus on implementing the actual scientific protocol, and that's it. And also it would be good if the computer language we need to use to code our protocol is simple and concise enough that can be easily understood by the developers, say 1 year later, which is not trivial, but also by other people, or and also ideally it would be good if such code could be easily also modified and extended so that the work can be reused over time. And these last aspects around productivity in writing the pipeline are really hard to handle when using just plain scripting languages such as Bash. And I think that Costa later on will probably show you some more detailed examples around this specific aspect. And so here, this is very broad. Still, there are a couple of technologies that we identified as quite good helpers. So containers is on the software stack side. I'm not going to cover that today. I'm just going to mention it on these slides, and that's the end of the story for today. And then scientific workflow engines or systems for the pipeline aspects that I mentioned to you. And so this type of tools, hopefully, are the ones that are able to simplify the design and deployment of workflows. So that the research, as I mentioned before, can focus on just writing and developing the backbone of the pipeline, so the structure of the tasks you need to run, and eventually just specify the configuration that can be machine specific, say Slurm at Pawsey or PBS on NCI and other things like that, or deploy with containers, deploy with modules, software-wise, and so on. And the tools would take care of all of the other generic aspects to the pipeline. So there's really, especially in bioinformatics, there's a huge variety of tools available out there. These are just really 5, but there's literally more than 100. Nextflow and SnakeMake are worth a mention because they look like that these days they are the most common, especially on command line based pipelines. Galaxy is also quite popular in bioinformatics, but it's a GUI based tool. It's a web browser based, and right now it's really mostly targeting bioinformatics. It might change in the future, but that's also an alternative we're mentioning in the space of graphical workflow engines. So today we're going to focus on Nextflow. The reason is that myself and a colleague a couple of years back, we did a trial on a few of these technologies, and we identified it as well. Back then, it was one of the best featured ones. And I'm going to go through some of the benefits of Nextflow today with you. With that being said, other engines are often comparable. I'm still trying to highlight for you what are the key advantages of Nextflow specifically. So from now on, I'm just going to try and introduce to you a few of the key concepts involved in developing a pipeline with Nextflow, and meanwhile, show it to you as a live demo so that you kind of get a real sense of these concepts. So in the Nextflow jargon, the tasks that you need to run are defined as processes. So they're basically wrappers around, say, a specific command line that you need to issue to run a specific task. So there can be a script, there can be a snippet of code. So Nextflow is written in Groovy, so you can even code some of these tasks as bare-bone Groovy snippet. Sometimes it can be handy, but Nextflow otherwise can implement Python, R, really any other language, and can also execute command line applications. In a process wrapper, you typically have to specify the input and output that are required to that process. They kind of represent the interface for the process towards the rest of the pipeline. Then you call them process when you define the template, so the generic action you want to run. But then when you instantiate them, you call them tasks. This is just the Nextflow jargon. So you may have one process definition, you have 10 input files, and you spawn 10 tasks out of the process. And one nice thing in Nextflow, by default, all of these runtimes are sandboxed. So each task gets its own isolated directory in the file system. It runs independently from other tasks, which comes pretty handy, especially when you're running the pipeline at scale over many samples, because you basically take out the risk of overwriting files among different pipelines you're running at the same time, eventually from the same directory. So this can be quite handy. It can also be quite handy for debugging, because you can just point to the directory where that specific task ran and debug it. And this type of approach also enables modularity at the level of the design of the pipeline. So in the way you actually write the pipeline itself. So it improves readability of the final script. I'm not going to touch much on this, but I think Costa, the examples that Costa is going to show will make use of modularity. Then there is this concept called channels, which basically abstract away the connections between processes. And this is kind of different to other workflow tools I got to know, because other ones such as SnakeMake, but all of the other ones really, they just handle the passing on information between processes as files. So everything is just a file. And one might wonder, why abstracting this? Why adding one more layer? Well, that's really quite handy, because it allows to handle this data transfer in a more general way. It allows to naturally scale the pipeline from 1 sample to 100 samples, and it behaves the same way. It also makes writing of the pipeline more natural and more concise, more readable. And that's because you're not thinking in terms of files, but really in terms of chunks of data. And it also enables one very powerful feature of Nextflow, which is called operators, which I'm going to get back to you probably in a couple of slides. But in general, it's just a way of manipulating data. Again, it doesn't sound very exciting at this stage, but hopefully I'm going to show you a couple of examples. So processes and channels, they are the backbones of a pipelines. Then starting from, I think last year, there was this upgrade in the specification of the Nextflow language, DSL2. They introduced an explicit workflow definition, which...
So we define DSL as domain-specific language.
Yes, so it's, yeah, thanks, Costa. So DSL stands for domain-specific language, and 2 is because it's at the second iteration of the language specification of Nextflow. So the rules of the syntax that you use when you write the pipeline. With the updated one, which is now the default, you get to write explicitly the pipeline, again, in a very concise way, and I'm going to show you an example very soon. And then the final little bit before the first bit of demo is pipeline parameters. So Nextflow is a very, again, handy way of introducing runtime tunable parameters in your pipeline. With these very first concepts in mind, I'm gonna move to the terminal. So just a sec, because I've lost the screen again. All right. So let me make the screen a bit larger for you. I think this should be fine. So here I'm on Zeus, on the high throughput cluster here at Pawsey. Let me just load a couple of things that will be useful later on. One of them is the Nextflow module. So the examples I'm going to show you today are available on GitHub, and there will be the link in the slides, which I can share with you after the webinar. So in this GitHub project, there is a Nextflow sub-project, and here we go. This is the first one I'm going to show. So let me show this .nf file, which actually is the pipeline file. And you can start and see some of the things I mentioned to you earlier. This is a very silly pipeline. It's really a demo pipeline. It doesn't use files. It doesn't use any program. It just handles text manipulation in a very simple way. But it's important to just have a look at how these processes are defined. As I told you before, there is the script definition that in most cases can just be a bash snippet. Here I'm just using echo and Linux stuff because it's a simple example, but there is where you can put, I don't know, blast, or OpenFOAM or whatever application, command line application you have developed and you need for your pipeline task. Then there's ways of defining the inputs and outputs. And that's, as I mentioned, that's how you tell Nextflow how this process can interface with the other processes. I'm not going to enter details of the syntax today. The key aspect is just the need for defining inputs and outputs in a formal way. And in this pipeline, we just have a couple of processes. The other thing I'm going to show is the workflow definition, which is this block here. So the first bit is where you tell Nextflow where to grab the inputs. And with the new syntax, this is basically typically the only place where you notice channels explicitly. Channels used to be a huge thing in the, I mean, you notice the channels all the time in older pipelines. They were also a source of confusion and ambiguity and difficulty in coding. Now with DSL2, they have hidden them under the hood very well. So this is the only place where you're going to see the channel keyword in this pipeline. And basically, you're going to define this text channel that grabs information from these parameters, which is defined above. And then once you've defined your text channel, you're going to use it. And so split letters was the name of the first process that I defined above. And then you just say split letters from the text channel. And then suppose you need to process the output of this with the next process, which is convert to upper. Okay, convert to upper, what? Well, you convert to upper the output of the split letters process, right? And so that's how you define the logic. That's how you connect the pieces of your pipeline together. With this type of syntax, you define the input channels and then you start and use their names to specify the inputs needed by different processes. And this is just a hint of what an operator looks like. So these are just a set of available keywords that you can use to manipulate data in your channels. And in this case, flattening means I have a list of items, and the list is a single object. Now I want to flatten the list, which means from one item list, I want to make n single items. And you start and probably realize that's a common pattern when you develop pipelines. Now it's flattening a list to single items. Then tomorrow it's mapping a set of items to a function. Then it can be a reduce of 100 items to a single output. Then it can be a mixing of two different input types. So you have 10 input data sets and one reference data set, and you need to make the Cartesian product of them. So just to give you 3 examples of what an operator is. It's common ways of manipulating data. And Nextflow has coded, I think it's about 30 or 40 of these common ways for you to keep the syntax concise. Now, you can't remember them all, but the documentation is really beautifully written. So you have this single web page in the Nextflow docos where you can go to as a reference page to answer your question. Okay, I need to do this data pattern, this data manipulation pattern, which keyword I need to use, and you go there, and that's it. And you have this very concise definition for your pipeline. And then, okay, in this case, there is a very last step is actually just a visualization step. So you take the output of convert to upper process and you want to view it, right? And this streaming is you can forget about it. It's just about getting rid of some new lines in the output. It's not really important. In the end, it's just another example of applying operators to an output channel. So you saw how by defining processes and they are named, and then by connecting them together in a workflow, eventually using an operators here and there to manipulate data in common ways, you can build up a workflow. And I'm going to run it in a minute. Before doing that, just going to show you what that input source was for the original, for the start of the pipeline. It's this one. It's just a string, hello world. And that's this params.str. And in fact, now I'm jumping back to the end of the pipeline again. That's what I'm using, param.str, as the starting point for the input channel. And let me show you how you use this script with Nextflow. So you can go Nextflow run. I don't need any specialized software now because it's just Linux commands. And basically what the two processes done together is to chunk the sentence in the single words and then make them uppercase. It's silly, but it's just a way to show that it's happening. And you get some logging on the screen for that. You also get some other logging if you want. So there is a splitting process, which takes the original sentence to split it. But then the sentence has 2 words. And then you end up with 2 convert to uppercase processes, each one processing one of the words that come out of the first process. And then the nice thing about the tunable parameters that I mentioned to you, any params that you define in the pipeline can be changed at runtime, and you just use the parameter name with this flag syntax. So I can say now it's a 4-word sentence. And in fact, you see that now we have as many as 4 convert to upper processes that have been spawned, because that's what the second process gets as input from the previous one. And you also, okay, so now the output are still in order, but if I were to write a longer sentence, at some point you will see that the output will, the order of the output will not be respected, as you see here. And that's because that's not a requirement in my pipeline. There is no required order of processing. All of those convert to upper processes have the same hierarchy in the workflow. Of course, there are ways of changing that, but otherwise the pipeline runs in an asynchronous way when tasks have no dependencies with each other. So this was a very simple one. Let me get back to the slides and just introduce a couple of more concepts, which will show you how to run real applications inside processes. So a little mention around integration with containers, but this also holds true for software modules or Conda deployments. Nextflow has a very nice interface with all of these technologies, and this is probably one of the best ones in this regard. So it has containers, Kubernetes, it has, as I said, Conda and modules. It's also gonna get support for spec, the package manager, very soon. So which means you don't need to know how to install stuff with these. You just specify, say, the container name, and Nextflow will use it. And the other nice thing that I think it's a bonus feature is Nextflow is the possibility of clearly splitting the definition of the pipeline and its parameters from the configuration that is specific to a given machine, which means, so if you don't have to, but you can, and you almost always can, which means if you do things carefully, you end up with a scientific workflow coded in a script, which you never have to touch unless you have to change the protocol. If you need to redeploy to a new machine, you only edit the configuration file. And that makes it very understandable, very maintainable in a way, and easily portable to other systems. And okay, this is just about operators. So with these new concepts around using containers and deploying with configuration files, let me go back to the terminal.
Just to skip some of them because we lost some time a little bit.
Yeah.
Maybe
yeah, well, I will keep it shorter to the end. Yeah, thanks, Costa. So let me go to another example, which is now it's a small bioinformatics example which uses a package, which is called BLAST, which is quite common in bioinformatics pipelines. So let me run it first, and then we'll comment on that. So the file is called blast.nf now. And if I run it, spoiler alert, will fail because there is no BLAST installed on the system. So now what? Well, now I say, okay, Nextflow, you use Singularity to run this in containers. Now, I did a few things yesterday just to save time, but this still works. So it just ran just by enabling the usage of containers. And so now you see I ran my processes, and if I now do an ls in the directory, there is an output file that was created. How did I achieve that? Well, I didn't have to touch the pipeline file, as I kind of just mentioned in the slides. I just worked on a configuration file, which normally by default is called nextflow.config. Let's focus on this one because it's the key one. This standard profile was what was used in the run, and all I had to do, well, was not super minimal as I promised to you, but almost. So I had to tell, okay, for running the processes, you may want to use this container, and I just gave the container name. Then I just said to tell Nextflow how to find Nextflow in the system. And Nextflow at Pawsey is in the form of a module. So you had to say, okay, use this module to find Singularity. And then, yeah, this is where it gets already a bit machine specific. I didn't have to, but to save time today, I used a cache for the containers. Otherwise, I would have had to wait until the container was pulled from the internet. But just to say, this was not mandatory. This was mostly just to save time. So at bottom end, I specified a container to use, and they said, okay, if you need Singularity, you load this Singularity module. And so when I did that, the moment I told Nextflow, okay, run with Singularity, it just turned Singularity on. It knew which container image to use with Singularity, and that was it. And the job could find could find Blast in that container, and that was the end of the story. And that works in a similar way if you're using software modules or Conda or Docker containers. And the very last thing, because then I want to hand over to Costa, is still around a couple of extra bits. So the Nextflow, and again, Nextflow is quite better than other alternatives in this regard. It has interfaces for lots of schedulers, so Slurm, PBS, but also others that I can't recall, but also cloud services, AWS, Google Cloud, Azure, Kubernetes. It means that it provides a simplified interface for you. You don't have to know all of the syntax for these frameworks. You just specify the minimum amount of information that you need, such as the core count, the wall time, this type of stuff. And the very last thing that you kind of saw already in my config, profiles. So you can define multiple ways of running the pipeline, and that's how you maintain different configurations for different machines. And that's probably my last bit before I hand to Costa. Then I'm happy to take questions at the end of the webinar. My last bit is just, let me reopen the config file. So there was this standard configuration, but then there was also a Zeus configuration. Zeus is the name of the cluster on Pawsey. And the Zeus configuration, without entering in too much detail, just says, okay, always use Singularity, always by default. That's how Blast is available on Zeus. And also use Slurm. And then there is a bunch of definition for Slurm, but which is mostly really, okay, 1 core, 4 gigs of RAM, 5 minutes on the work queue. You don't need to know almost any Slurm syntax. You just need to know what your process needs from Slurm. And how to use this? When you do your Nextflow run Blast, you specify the profile. You say, okay, use the profile Zeus, not the standard one. What was that? It's the beauty of the...
I think it's use one.
Yeah, I think you're right. Yeah, thanks, Costa. So you do that, and what's happening right now? I can't. Maybe I can show you because I have another. Here we go. I have another session open on Zeus. Now it's using Slurm, so it's spawning the very same process as before, but as Slurm jobs, and that's just by adding those few lines of Slurm specification in the config. You need to go to NCI. You do the same thing for PBS and similar things. That's it. There's much more to that in Nextflow. these are just the basic concepts. Now I think I'm gonna hand over to Costa for a demo or with for a real life pipeline. I think there were just a couple of questions before doing that.
Your thing over.
I think we can.
Oh, can you do?
I don't know. I can share.
I will unshare just if there's any
Just
pending questions.
Does Nextflow need to be installed on your worker machines as well, where you like running?
So it needs to be installed. It's very lightweight. It only needs a Java runtime, and that's it. It's really just literally a curl download from the internet. So it's lightweight. Typically, at least at Pawsey, we ask people to run Nextflow, even the master script of Nextflow in a job queue, because it will go on for quite some time. And some of the operations might be memory intensive if the operators handle large chunks of data and do manipulations. So it's always a good thing to run the Nextflow master pipeline, not as I did today. This was just a small example, but to do it in a scheduler script. And then at that point, Nextflow will need to be installed in the compute node where it will be run. But it's a very lightweight installation.
No.
What?
The answer is no, you don't need to install it. I would just answer adding to your answer that you don't need to go and install it in the worker nodes.
You do. You do.
On a driver node you need.
Yeah, but
it will create a shell for you.
But what I'm saying is that you need to run Nextflow in a worker node at Pawsey. What I did was wrong.
The setup for the memory limits and trying to use the appropriate resources. But also right, if you're just launching Nextflow on a general cluster and they have login nodes.
Okay.
Memory, it spawns scripts that have DOM dependencies. It doesn't run.
Okay. Yes. Yes. Right. Yeah. Yeah. Sorry. Yeah. Okay. Yeah. I didn't get the question.
But typically, because it could do some memory intensive stuff, it's good that you actually launch it in a script.
Yeah. So you need it just for the master. The child processes don't need to know about Nextflow.
But all machines that you can use, but can't necessarily like install stuff on easily, but
Yeah.
you can still run it.
Yeah, I mean, for the child processes, you only need the actual application you need for that process. What I was saying is that typically would run Nextflow at Pawsey from a Slurm script, as you see there. And then for this typical scenario, you need Nextflow on the worker node as well. But that's only for the master process.
All right.
Thank you. I'm unsharing and handing to Costa.
All right. Hi, everyone.
Just share the perfect.